So good morning. I am Krishna Kumar, speaking from Krishna's class. Today we continue with our explorations of diagonalization. And we have in the last class developed a kind of strategy for doing this. The strategy is to exploit to the maximum our computational skills on matrices, because we have seen that given a linear transformation T on V, where V is finite dimensional, I have put the basic conditions here. I am assuming the space is of dimension n and be a ordered basis. One can construct a n by n matrix operating on Fn plus 1. So T has a representation as a map from just recall that the choice of the ordered basis sets up a isomorphism between V and Fn plus 1. And then you have the picture as follows. Let us draw a little diagram here. That is just the diagram that we are used to. So T is a linear transformation on V. And once we choose an ordered basis, it sets up a isomorphism from V to Fn cross 1. And then corresponding to T, you have a n by n matrix, which we have designated by T B, which maps the image of V in Fn cross 1 under the isomorphism set up by G. So let me call that X, and this is actually the instead of X I can write here V with respect to V. So TB maps the representation of V with respect to B in Fn cross 1 to TV B in Xn cross in Fn cross 1. This is an n by n matrix. We have also observed that both T and the matrix TB has the same set of eigenvalues. And once we know the eigenvectors of TB, we can pull it back by using phi inverse to B and find the corresponding eigenvector of T. Therefore, analyzing TB and finding out its eigenvalues and eigenvectors is the option that you have here, because you know how to go back to B, because we started with a ordered basis here, and so we know how to go back here. Okay. So the problem boils down to finding out the eigenvalues and eigenvectors of PV. Okay, so let us just note it down. So we have V, introduce a ordered basis V to go to F n cross 1, and then we have the mapping from V to V given by T, and there is the corresponding map from Fn cross 1 to Fn cross 1, which is designated by T B, which is an n by n matrix. And this again. So this is the diagram that we have drawn. And therefore, now we concentrate on the map from Fn cross 1 to Fn cross 1. We don't bother about this for the moment, because we know that once we resolve things here, we can always go back there. So, if lambda is an eigenvalue of if and only an eigenvalue of T. This is the most important connection between the two. A second connection is therefore, see, the eigenvalues are in a way invariant under getting the matrix representations. Irrespective of what matrix representation you get, then all these matrices have the same eigenvalues as long as it represents T. Okay, so this is the scenario that you have. And then we found that once you get the eigenvectors, you can always get the corresponding eigenvectors of T. Okay, once pull them back, V to get the eigenvectors of once again, suppose we have sufficiently many, that is n eigenvectors of TB such that they form a basis for Fn cross 1. Supposition. Then we have n linearly independent vectors in V which form a a basis for V, and which are eigenvectors of in such a case, in such a scenario, if we choose these eigenvectors say V1 prime, V2 prime, Vn prime, respectively belonging to the eigenvalues not all is different as an ordered basis say V prime defined by V1 prime etc. Vn prime, then we have Tbi prime equal to lambda I Vi prime. And is diagram. That is some of these eigenvalues may be repeated. Okay, so this is the strategy for solving the problem. What we do is choose a convenient ordered basis B for V, find the matrix representation of T with respect to B, then find the eigenvalues and eigenvectors there, then pull those eigenvectors back to the vector space V, and if those eigenvectors are sufficient in number, namely n of them, which are linearly independent and forms a basis, then their pullback also form a basis for V. With respect to the new basis that you have designated by V prime, we see that we have the equation T Vi prime equal to lambda I Vi prime, the same lambdas that are occurring as eigen values of the matrix TB. And then if you write down the matrix representation of T with respect to B prime, it is diagonal. So this is the story. So this is all you know, conditional, namely with several conditions. So it starts from here. So we have a supposition which sets out all the conditions for getting a diagonal representation. Therefore, now we can define when T is diagonalizable. That's the first task. So let us write down. So we shall give the definition. T is diagonalizable if there exists an ordered basis B prime where each right. So the important thing is that we get an ordered basis for B consisting of the eigen vectors of T. So the central question that we ask here is, does it happen always? That's the question that we ask. If it happens, then we would have everything diagonalized. Let us look at the complexities of this problem by looking at some examples. And that's the best way to get insight into the problem. So let us start with the example. Let's consider the following examples. The first one, we take the simplest possible scenario, we take B itself to be so R2 is a vector space over R. Therefore, dimension of B is equal to 2. And we have the standard basis. E1. If you want, you can put R2 cross 1. So let me do that. Fn cross. So that this is Ei equal to. Therefore, we have the following situation, namely E1 equal to 1 0, the column vector 1 0, and E2 equal to the column vector 0 1. So what we have is the following. So we write E1 equal to this form of basis. Now let D be defined by P of equal to zero. Minus x to x1 for every x equal to x1 x2, which is equal to x1 into 1 0 plus x2 into 0. This means that T of E1 equal to so E1 has x1 equal to 1 and x2 equal to 0. So you have 0 T of equal to x1 equal to 0, x2 equal to 1. Okay. So what about the matrix of T? This is equal to by your definition, this is So, this we have obtained the matrix representation. Now, what you have to do is to find out the eigenvalues and eigenvectors of this. What do we have to do? Lambda is an eigenvalue that is all lambda belonging to R, that is associated field that we are taking, for which lambda I minus if you want, it's not necessary. I is the 2 by 2 identity matrix. Is singular. And this, you know, is equivalent to the condition that determinant of equal to 0, and that is, you can only, what is lambda I minus t? This is equal to lambda 1 minus 1 determinant of this equal to 0. And that happens if lambda square plus 1 equal to 0. Let us see finally. So it is true only for those lambda for which, so the eigenvalues are essentially those lambda for which lambda square plus 1 equal to 0. And there exists no real number which implies there exists no eigenvalues for T so clearly if there are no eigenvalues, there are no eigenvectors. That is, we cannot find eigenvectors T since they do not exist. So there are no eigenvalues at all for this problem. Okay. Let me slightly modify the code and then find out what exactly happens. So let us modify the code. Now you know that the problem that you have is that lambda square plus 1 equal to 0 has no zeros. Now this is exactly the characteristic function associated with t. Okay, so what you call it, lambda defined by the characteristic polynomial of t. So the characteristic polynomial has no zeros in R. This is the problem. Now when would this have zeros in a field? Now you see that if you change the field, to C, but then if you change the field, you know that R2 over C is not a vector space. Okay. Therefore, we have to change the vector space also. Suppose we take the vector space to be C is the complex field in cross over C. Now we are having both x1 and x2 as complex numbers. Okay, so we have the same kind of analysis. Then the characteristic polynomial namely which remains the same. There is no change at all as you can go through this analysis. So here you have dimension of V, which has roots in C. As anyway, you know that C is algebraically closed, so there exists roots for any polynomial with, in fact, all the roots of any polynomial with complex coefficients in C itself, and that is the fundamental theorem of algebra. The roots are I, comma, these are the two roots. So we will take lambda 1 equal to I, lambda 2 equal to minus I. So we take lambda 1 equal to I, okay. Then what do you have? See, I is an eigenvalue of t. So let us compute the eigenvectors. So what we have is this. With lambda 1, for lambda 1, we compute the eigenvector. So what we have is this. We have to look at this equation, lambda I minus so let us write it up. So if I write x to be x1, x2, then I have the following equation. That is 0 minus 1, 1, 0 of that gives the following equations. If you compute this, then you get two equations, namely minus x2 equal to ix1 and now you see that both these are the same equations, because if you multiply this by I, then you get this equation. Therefore, essentially there is only one equation. There is only one linearly independent equation. Therefore, let us choose. So the solutions are there exist non-trivial solution. That can be easily obtained here because both these equations are the same. One of the vectors you can choose, one of the components you can choose arbitrarily and the other one will get fixed. So let us choose therefore the corresponding vector is then 1 minus. So we have the property that I minus or PB x1 equal to x1. It is PB that is one vector. Now similarly for lambda is equal to minus I, which is the other eigenvalue, we have the eigenvector equal to you can easily check that or C. So C2 cross 1. Okay, I made a mistake there earlier. So it is C2 cross 1. So no, this there was a mistake. Okay, doesn't matter. Now it's clear. Just a slip on my part. Okay. Therefore, C2 cross 1 is a vector space spanned by these two vectors. Okay. Therefore, what is the diagonal representation of T? So let x1 x2. Then what do we have? Let us find out what it is. E of one minus 1. This is equal to, what is it? This is equal to and D of 1i. Therefore, P of x1, x2. You can write this x1, x2 split up in terms of 1 plus 1, 1 minus I and 1 plus I. Okay, so let us do that. Okay, therefore now we can write down the matrix of this. Okay, right? Therefore this is equal to matrix of T with respect to this is equal to I. That's the diagonalization. Therefore, T is diagonalized. So what we infer is that T is diagonalizable as a linear transformation on C2 cross 1, but it is not diagonalizable on R2 cross 1. T is not diagonalizable on over R, but is diagonalizable is diagonalizable on so lot of things are involved because this example gives lot of insight. What is the insight that you get? First of all, the field may play a role because the existence of eigenvalues may depend on the field. Okay, because you are searching for the solutions of the characteristic equation, which may not happen in R, or which doesn't happen in R, but it happens in C. But in that case, you know that R2 over C is not a vector space. Therefore, you will have to repose the problem on C2 over C. So that's something of an insight into the problems that you may problem. Now let me do another example. In fact, many examples will give you a lot of insight into the difficulties, and then we will have to work out to handle such difficulties. It's not that all T's are diagonalizable. Depends on several factors. Now let me look at this example. This particularly I do it in a hidden space, sort of disguised camouflage space, so that you get into good insight. Our rotations will be clear from that. Okay. Let me take V to be that is all polynomials of degree less than or equal to 2 along with the zero polynomial. Okay, and you know that this is the dimension of V equal to so a typical member of V2 or V is, we call this Px, then Px is P0 x squared. So as we have explained earlier in the general theory, you start with an ordered basis which is very convenient to handle. Okay, so let us take write B, choose B as you know that this is a linearly independent set of polynomials of degree less than or equal to 2. B is A. Now let T from be defined by, see, you need say what it does on the ordered basis. So then T is completely defined. So let us define that P of 1 equal to 1 plus 2x plus 2x squared and t of 2 plus 2x. If you want, you can put 0 x squared. Okay? Then you know that is given by the matrix, the 3 by 3 matrix, 3 minus 1, 3, 1 minus 1, 2, 2 minus 1 and 0. So what I am doing is writing down the coefficients 3, 2, 2 as the first column, 1, 2, 2 as the second column, and minus 1, 0 as the third column. Oh, I'm sorry, I think here I have. Minus 6. This is how it is. Minus 1, 0 as the third column. So this is the definition of the x squared. Okay. Now you know that this is a linear transformation on V. I mean, all those things you verify, because at least at the learning stage one should do a lot of computations to understand this. So we have obtained TB, and you know that TB is not diagonal. But it doesn't say, I didn't say that it is not diagonalizable or anything, but at the moment it is not diagonal. So what do? We try to diagonalize this if possible. Does there exist an ordered basis B prime that's a question. So it is pretty straightforward what we are looking for. What we are looking for is whether this can be diagonalized. This matrix can be diagonalized. What do? We look at this problem, whether whenever I write I here, it is 3 by 3 identity matrix in F3 cross 1. What values of lambda, for what lambda is zero. is the question that you are asking. This is, so let us find out the characteristic polynomial of T. Or I would say that this happens we require determinant of equal to 0. So we have to determine lambda such that this is true. Now if you simplify, this is what you get. This turns out to be what is called the characteristic polynomial. The characteristic polynomial is polynomial of T which is also the characteristic polynomial T set to 0. And if you simplify this, you get f lambda. This is the characteristic polynomial. I was just checking whether computations are right. Well, you can explicitly compute it and see what that this is. Therefore, the eigenvalues are zeros of f. So what are the zeros of f? Lambda equal to 1, lambda equal to 2 are the eigenvalues of T. So let us write now. See, we have got two zeros of the third degree polynomial and one of them with multiplicity 2. So lambda 1 is a zero of algebraic multiplicity polynomial. One and lambda 2 is a zero of algebraic of T of algebraic So these are the situations that you have. It's not clear at this stage whether you can get an ordered basis for V such that the algebraic multiplicity of V such that it forms a basis for V with respect to which this would be time. Let us explore this. Now let us compute the eigenvectors. This is done easily because what you do is you require first for lambda 1 equals 1. See, what you have to do is, see, you have to look at lambda, that is I minus equal to 0. That means TBX equal to X. Let's find it out. So what one gets here is that the null space of, essentially you are looking at the null space of I minus TB. Now this turns out to be simply, so I just do this for this case. In that case what you get, you are taking lambda 1 equal to 1, so you get minus 2 minus 1 minus 1 then minus 2 lambda equal to 1, so minus 1 1 and then, sorry, this one is there, then minus 2 minus 2 1. These are the three equations that you have to solve. Okay, so let me do it. So I have two independent equations because the first row, when you multiply, you will get minus 2x1 minus x2 equal to 0, and the same equation comes here when you multiply this x1, x2, x3 by this second row. The third row is minus 2 minus 2 minus 2x1 and minus 2 x2 plus equal to 0. So we are looking for solutions of this. There are three unknowns and two equations, so it's a underdetermined system. So there are plenty of solutions for this. In fact, there are infinity solutions do exist. And let us conclude that. So one observes that, you see, if you simply subtract, you will get x2 equal to 0. Okay. You will get x2 equal to 0, and then you have the same equation minus 2x1 plus x3 equal to 0. So we can choose x1 or x3 arbitrarily. So let us choose x1 equal to 1 and then x3 equal to so the null space of this is equal to span of the vector x1 equal to 1, x2 equal to 0. Okay, so there is one non-zero vector or 1, 0, 2. Incidentally, you can observe that every scalar multiple is also a solution of the same. That is why this is a vector space. So this is a subspace of that is expected because it's an eigenvalue, so this is an eigenvector. So 1, 3, 1, 1, 0, 2. In fact, any scalar multiple of that is an eigenvector. So let us now proceed with the next eigenvalue. For lambda equal to 2, let us compute. For lambda equal to 2, do the computation for lambda equal to 2. Then what you have is, you have to look at 2I minus TB. We have to solve this to get the corresponding eigenvector. How do you compute this? That's quite easy. Let us write down what it is. Okay. So this is equal to minus TB is I don't have the computations readily available. This is equal to, this is 2I minus TB. This is equal to minus 3 plus 2 is minus 1. Minus 1, 1. then minus 2, and then 2 minus 2, 0, you have 1, then minus 2, minus 2, and then therefore what we want is this. So to solve them, you get how many equations? You get two independent equations. So what are the independent equations that you get? The two independent equations are, okay, minus x1 minus x2 plus x3 equal to 0. Then you have the third equation is exactly the same as this, except for being a multiple of 2. So minus 2 x1 plus x3. So let us choose, see, one of the variables x1, x2, x3 you can choose arbitrary. So you choose x3 equal to, then what do you get? You get from the second equation. Oh, let me choose x1 equal to. I don't want fractions to come. Then you see that x3 equal to. So you see that and what about the third relation? Or we have to have the other relation also taken into account. So you get minus 1 minus x2 x3 is equal to 2 equal to 0. Therefore this gives, therefore the vector that you get is this. x1 is arbitrarily chosen, 1, then x2 equal to 1, and then 2. So this is an eigenvector. Okay? Therefore, one, 2, associated with the eigenvalue two. But the algebraic multiplicity of 2 is, of the eigenvalue 2 is 2, whereas there is only a one-dimensional vector space associated with 2. So let us make note of that. Follow the algebraic multiplicity. So the algebraic multiplicity need not, and there is no way in which you can get another eigenvector. So the algebraic multiplicity of an eigenvalue need not be equal to the dimension of the null space associated with it. Okay. In short, to stand in fact, you need three linearly independent vectors which are eigenvectors. Therefore, in the absence of this, P is not diagonalizable. This is a problem. So you do not have enough, and consequently P is also not diagonalizable. What are the eigenvectors of T? See, T acts on the polynomial space. So we have to get it as polynomials. For T, lambda 1 and equal to 1 and lambda 2 equal to 2 are eigenvalues. Then we have the polynomial. So P1, we are just translating this, what is that, the eigenvector corresponding to lambda equal to 1 to this. So you get P1x is in that case 1 plus 2x. Is the eigenvector. I should not write the eigenvector because all scalar multiples of that. It's an eigenvector. Similarly, and that is the only thing possible. Okay. Now for lambda equal to 2, the corresponding eigenvector of T, the corresponding eigenvector of T associated with What is it? It is going to be 1, 1, 2. 1, 1, 2 is actually 1 plus x plus is P2. Now the dimension of the corresponding eigenspace is equal to 1. Okay? The dimension of the eigenspace corresponding to lambda 1 is 1. The dimension of the eigenspace associated with the eigenvalue 2 is also equal to 1. So this is the scenario that you have. Okay? Dimension of So we don't have sufficiently many eigenvectors. So this consists of all the possibilities. Eigenvectors. There does not exist V of V consisting of eigenvectors of hence not eigen. So let me just sum up. This particular example gives you two eigenvalues, 1 and 2. 1 has multiplicity, algebraic multiplicity 1. 2 has algebraic multiplicity 2. However, their eigenspaces are both of dimension 1. Therefore, we get only two linearly independent eigenvectors of T. That does not span your three-dimensional space. Therefore, T is not diagonalizable. Okay? So it's not that always T is diagonalizable, even if you have, enough eigenvectors. Sorry, enough eigenvalues. Okay, right. So that throws some light into the type of problems that you are going to encounter. Okay, let's take a third example. Now, a third example I want to take up is the following. Once again, I take the polynomial space. Then what to it. And the third example I take is the following. Now I think my computations are right. Okay. The third example is this. Again I take V to be equal to dimension of V. Now let me take P of say let me take V equal to, that is almost a simple choice that you make for computations. And then what you have is this. Let us define P of 1 equal to P of x equal to 4 plus 8x squared dx squared equal to, these are the definitions. Four plus 4x squared. So minus 9, minus 8, minus 16. So this gives, then computes to be, I'll be leaving all the computations to be, in this case, minus 9, plus these coefficients will form the first column, minus 9, minus 8, and minus 16. Then 4, 3, 8. That is, these coefficients will form the second column. The third column is going to be 4, 4, 7. Now you can compute the following. Exactly as we did in the previous case, we proceed and we find out the eigenvalues and eigenvectors of T. So eigenvalues of, you can see that what you have to do is, the characteristic equation is the characteristic polynomial is given by determinant of lambda I minus b, where I denotes identity matrix in R3, and this works out to be lambda cube minus lambda square minus 5 lambda minus 3, which factors into therefore there are two distinct eigenvalues. Lambda 1 equal to minus 1 with algebraic multiplicity two, and lambda 2 equal to 3 with algebraic multiplicity. There are two eigenvalues. Now let us compute the eigenvectors corresponding to that. So for lambda equal to minus 1, if you compute lambda I minus a, or works out to be 16 minus 4 minus 4 minus 4 minus 4 minus 8 minus 8. Therefore, x1 minus 4x2 a single equation, because all these equations are the same. This is the scalar multiple of the other. There's only one equation, where of course x is equal to. Now this provides you with solutions, two linearly independent solutions. So this gives essentially 2x1 minus x2 minus x3 equal to 0, and you see that one, 0, 2, and independent solutions. Therefore, the eigenvalue lambda equal to minus 1 provides you with two linearly independent functions. Similarly, we work out the eigenvector corresponding to the other eigenvalue. 3. We have 3I minus this is equal to 12. So there are two, the rank of this matrix is equal to 2. Therefore the nullity is equal to 1. So you have two equations to simultaneously consider this. That is, so if I factor out, this is the, so I am looking at this 3I minus zero. So I get two equations to determine the components of x. They are 3x1 minus x2 0 and 2x1 minus x3 equal to 0. Corresponding to this, I take the factor out. The factor does not matter because these are homogeneous equations. Okay. Therefore, that gives the single solution. I mean, of course, one arbitrariness is there. So, one of the variables we can choose arbitrarily, the others we can determine automatically. So, we set x1 equal to 1. Then you get x2 equal to x3 equal to 2. Therefore, 3 minus 2, sorry, 3 minus 2 will give you x2. Therefore, the vector that you have to consider is corresponding vector is 1, 1, 2. So you see that the three vectors, so let me call them. So x1 equal to x2 equal to 1, 2, 0, x3 equal to spans V cross 1. And they are eigenvectors. Therefore, we get enough eigenvectors to span R3 cross 1. So the index is eigenvectors and form this. We invariably found that these vectors are all linearly independent. These eigenvectors belonging to two different eigen values are linearly independent. That's an observation that we make. We will make it. We will investigate this and we will prove for such things later. Accordingly, corresponding polynomials. The polynomial corresponding to x1 is corresponding to x1. So that is actually 1 plus 2x square d2x defined by 1 plus 2x are eigenvectors t belonging to eigenvalue lambda equal to -1. And P3x defined by one, 1, 2, is an eigenvector. Belonging to the eigenvalue and therefore one observes that these three eigenvectors do provide us with an order basis for P3. What are the in fact, you can easily compute the diagonal form. The diagonal form is what are the eigenvalues? B1 and B2 are associated with lambda equal to -1. So we have -1, -1, 0, 0, 0, 0, and then we have 3. That is a diagonal. Okay, that's a diagonal representation of PB. So this is diagonalizable. Okay, so we have looked at 3 different types of examples. One, of course, the first example that we considered, if we were considering it as in R2, then it is not diagonalizable, but in C2, it is diagonalizable if we take the field as C. The second example, in R3, you have sufficiently many eigenvalues. However, there is no eigenspace. Okay, so that's the problem. There are no eigenvectors which span the whole space. So it is not going to be anyway rectified even if you go to C3 over C or anything. The story will remain the same because you have got all the eigenvalues there. You cannot have more than 3 eigenvalues. And eigenvectors, you don't get sufficiently many eigenvectors to span the polynomial space. In the third example, we have found that we have enough eigenvalues and corresponding eigenvectors which span the whole space. And therefore it is diagonalizable. And there are many examples that you can work, but I suggest that you completely go through these computations. Okay? Now, from B you go to F. Okay, so how from V you go to F n cross 1 in the case of these examples. And then how do we compute the eigenvalues by looking at the matrix representation and computing their eigenvalues. And then how you pull back into the original space. That is why I have specifically worked with the polynomial cases in case 2 and 3, the polynomial spaces. Okay. So I think if you spend some time working out these details, I think that will be very good. Okay, we'll stop here today and we'll take up the story further ahead from next class onwards. Thank you very much.